was the mass rate balance. And so we're working on control volumes. And the first thing is conservation of mass, or the mass rate balance. And we're done talking about that. And now the thing that we have to get to is the first law of thermodynamics. Control volumes. So, okay, that's what we're on. First law of thermo. For control volumes. And I'm going to derive this. It won't take too long. And we're going to see that this derivation is where enthalpy comes from. Or this is why enthalpy is a thing. That's such a good quiz question. So remember that. Okay, so all the way up until we started talking about control volumes, when our system is a fixed amount of material, the first law of thermodynamics says, so the sort of conceptually, the time rate of change of energy is equal to the energy into the system through heat minus the energy that comes out of the system through work. Okay, so that's the equation that we're familiar with. But now our system is not going to be a fixed amount of matter. It's going to be a volume, and at any instant, we're looking at this volume while material is flowing in the inlet and out the exit. Okay, so now our system is a volume. You can think of that as like the inside of a nozzle or the inside of some device or something. And material is flowing in the inlet or inlets. Let's just call it inlet. And out the exit. Okay, so now how are we going to represent all the, the the conservation of energy equation for this volume? Well, so we're still going to have the time rate of change of energy. And now we're talking about the time rate of change of energy in the control volume. And that's still going to depend on the energy in through heat. That's increasing the energy, and then we'll be subtracting the energy that leaves the control volume through work. Now there's something new that we have to think about. So we have to think about adding the rate of energy carried in. That's going to be at the inlet. Okay, so if you have, so if at the inlet, at the instant you're looking at, there's a bunch of particles and they all have energy in all these different forms. They can have internal energy, potential energy, kinetic energy. And you move those particles into the system, that's adding energy to the system, right? The system now gets all that energy that those particles had. And you also have to deal with rate of energy carried out at the exit. And then there's one more concept that we have to think about. And that is, so you can have that control volume can be doing work on the surroundings if it's expanding, or energy can be coming in through electrical power or something. We've dealt with all that stuff before. But what we've never dealt with before is that the surroundings are now doing, the surroundings can now be doing work or vice versa at the inlet and at the exit. You can think of the material in the control or the cutoffs at the inlet and the exit of the control volume. Those are moving boundaries of material, okay? And forces are being applied from the outside. And so we have to deal with the work that's the energy that's added to the system through work at the inlet and the exit. So I'm just going to say this as plus the energy in at the inlet and the exit through work. And remember that the way that you calculate work, if you're thinking about a particle, is it's equal to the force that the surroundings are applying to the object you're looking at, dotted with well, and we're talking about rates. So you can think of this, the rate of work as the force dotted with the velocity vector. Okay. You saw that equation in physics 1 probably. Did you talk about it in terms of a dot product? Maybe. Okay. Well, so all that dot product means to us, for us, like these vector calculations are super simple. That just means that if the particle that you're looking at is moving in the same direction as as the force that's applied to it by the surroundings, you get positive power. And if that particle is moving in the opposite direction of the force, you get negative power. Okay, so we're going to use that to see what we can figure out about the inlet and the exit. Okay, well, so this is just going to be d dt for the control volume. The energy in through heat, that's still just going to be Q dot. The energy out through work, that's still just W dot. Okay, now what about the rate of energy carried in or out at the inlet? Well, since material is always coming in the inlet and you can't have negative energy, this is just always going to be positive. So what's the rate of energy carried in at the inlet? Well, that's going to be the energy that these particles have that are coming in the inlet are made up of internal energy and kinetic energy and potential energy. We can think of this as the mass rate at the inlet times the internal energy at the inlet. That's the total internal energy flowing in at the inlet, plus 1/2 times the rate of mass flow at the inlet times the speed squared at the inlet. What's that term? Kinetic energy, yep. And then plus mass rate flow at the inlet times GH. What's that term? Potential. Yep. And then carried out at the exit, that's just going to be the rate of mass flow at the exit times the specific internal energy. Shouldn't have a dot. Plus 1/2 times the mass rate flow at the exit times the speed at the exit squared plus the mass rate at the exit times GH. And I guess these H's should have an I and an E. That depends on where those are. Okay, everyone with me so far? All right, so the last thing that we have to deal with is the work done by the surroundings on the control volume at the inlet and the outlet. Okay, so let's think of this device like this. So this is the direction of flow. This is the inlet. This is the exit. And we'll just think about each one by one. So let's first think about the inlet. So the work done on these particles, we're assuming that all of these particles have a speed. So uh, all of these particles are moving. So if we're talking about this is like a blown up view of the particles that we care about right on that boundary. And they're moving this way. And now we have to think about what force the surroundings are applying to these particles. So how would you characterize the force that, so first you have to sort of orient yourself, like which side do we care about? This is the control volume. This is our system. We want to calculate the work done by the surroundings. So we're trying to figure out the force applied by the right side to this red disc. Okay? And the nature of that force is going to be the pressure times the area. So there's going to be, and so which way is that pressure going to be applied to that disc? Yeah, exactly. All it can do is push towards it. So we have a force like this, and the magnitude of that force is equal to the pressure at the inlet times the area at the inlet. And so what's the work rate at the inlet? Well, so the key thing here is that the velocity of the particles and the force of the pressure are both in the same direction. So this is going to be a positive rate of work. Okay? So the work rate at the inlet is equal to pressure at the inlet times the area at the inlet times the velocity at the inlet. Yeah. Mm-hmm. So yeah, in that case, you would have to, yeah, you'd have to do this all as a differential equation in terms of time. But and that gets a lot messier. But the lucky thing is, a lot of times, I mean, you're not so like if you think of turning on a machine and you're trying to do the thermodynamics. For a machine to run all day, it needs to basically achieve steady state. If it doesn't, like if it doesn't achieve steady state because it's heating up the whole time, it's not going to work as long as you want it to work in a lot of cases. So anyways, there are a lot of cases where your device is going to reach steady state and stay at steady state for most of the operating time. And so in cases like that, that's an easier thing to calculate. And the vast majority of the energy or whatever you're trying to calculate is happening during the steady state period. And so we're, oh yeah. Well, yeah, then you have to think a little bit about how fast it's varying. In a case like that, I can't imagine there would ever be a time that you wouldn't treat that as constant. You just change what the constant is because the rate is so small, the rate of change. Okay, so we got this, and it's positive. Okay, so that's good. Now we're going to do some fiddling, though. So now we're going to fiddle with it. Um, so remember that the rate of mass flow at the inlet or anywhere is equal to the area at the inlet times the speed at the inlet divided by the specific volume at the inlet. Just so you can follow this later. Remember that this capital V is a speed, not a volume. And so that says that we can replace the AV, so AI times VI is equal to MI dot times the specific volume. Okay. And now we can rewrite the rate of work at the inlet as, let me reorder. MI dot times PI times specific volume I. Why would we want to fiddle like that? To make it easier. That is why. That's probably always the answer. And why? But why does that make it easier? It makes it easier because we don't have a way to, like, we don't have equations or tables that give us the speed of a fluid given the other stuff. But we do have a table that gives us this in terms of other stuff. So we rearranged this, rewrote it in a way that we can just look up everything we need on the table to calculate the rate of work. So this is all stuff from the table. Okay, now let's do the same thing at the exit. Who thinks it's going to be similar? Yes, exactly. Who knows what the one step is that's going to be different? Yeah. Yeah, exactly. Yeah, exactly. Okay, so let's just think through it at the exit. Okay, so now we're talking about this disk. Okay. And this is the system on this side. Okay. This is the direction of flow. And now we're looking for the force that the surroundings apply to this. All of the red dash stuff is the system itself. So we want the stuff coming from the right to the left this time. And if the force is all coming from pressure of the surroundings, which direction is that force applied? Yeah, it's the opposite direction this time. So this force is the pressure at the exit times the area at the exit. And so this time, the rate of work at the exit, the sign is going to be opposite. Why is that? The velocity direction and the force direction are opposite this time. So you have pressure at the exit times area at the exit times the speed at the exit. This negative comes from the fact that um, the flow and the force are in opposite directions. And now we'll fiddle with it again. We know that um, the mass rate at the exit is equal to A at the exit times speed at the exit divided by specific volume. And so A exit times speed exit is equal to mass rate at the exit times specific volume at the exit. And so the work rate at the exit is equal to ME dot times PE times VE and negative. Okay, so now let's put all of this together. This equation gets sort of long. Again, this is all stuff that you can get out of the table. Well, not the mass rate flow. So put it back into the first law for control volumes. And you get dE dt for control volumes is equal to Q dot minus work dot for the, we're going to give that a CV because that's talking about the control volume itself, not the inlet and exit. We're doing those separately. Plus, if I pull out the, so now we're dealing with the term. Okay, so now we're on to these two terms where we're dealing with the rate of energy carried in at the inlet and out at the exit. We have m dot times all of these three things. So I'm just going to pull the, so for this one, it's going to be mi dot times a bunch of stuff in parentheses, and then minus me dot times a bunch of stuff in parentheses. So this is mi dot times the quantity. What do we have in here? Specific internal energy at the inlet plus speed at the inlet squared over 2 plus GH at the inlet. Why did I use H? That's a terrible idea because we're going to, H is enthalpy. Let's change that all to Z's. That's not going to be an important thing for us most of the time. But okay, so let's change that to ZI. Okay, so where did we see that? So first, when I first introduced what each of these terms are, you need to change the HI and the HE to a ZI and a ZE. And then the only other place is what I just wrote. Okay, so that's not so bad. So change this to a ZI. Okay, and then we have minus ME dot times the quantity UE plus speed E squared over 2 plus GZE that V is velocity, right? Speed, really. And now the only other two things we have to deal with are these two, the two works that we calculated, the one at the inlet and the one at the exit. So that is plus M inlet dot times pressure at the inlet times specific volume at the inlet, and then minus the ones at the exit, ME dot times PE times VE. And now let's notice that we have this thing, we have MI dot times a bunch of stuff happening at the inlet minus ME dot times a bunch of stuff happening at the exit. Might as well pull those inside. Those sort of fit that pattern. So we can rewrite this as dE dt for the control volume is equal to Q dot minus W dot for the control volume plus MI dot times the quantity UI plus PI VI plus VI squared over 2 plus GZI and then the one at the exit minus ME dot times the quantity U exit plus P exit specific volume exit plus V exit squared over 2 plus GZ exit. And there it is. This one over here is the specific enthalpy at the inlet. And this one over here is the specific enthalpy at the exit. Awesome. So why not rewrite it one more time? So dE dt, this is the real one. I'm not going to ask you to rewrite it any more times. So dE dt for the control volume is equal to Q dot minus W dot for the control volume, so that's not including the inlet and exit, plus MI dot times the quantity enthalpy at the inlet plus speed squared over 2 at the inlet plus GZ at the inlet minus ME dot times the quantity enthalpy at the exit plus VE squared over 2 plus GZ. Okay, so that's the first law of thermodynamics for control volumes, and that's why enthalpy is a thing. No, just because we pulled it out. So, you know, so if we distributed this through, we'd have m dot times h plus mi, m dot v squared over 2 plus mgz. Yeah, well, we made that substitution to get it into a form where we would have um, where we would have the mass flow rate for everything, so we could associate all these together like that. We did use that fact. We actually used it in the reverse direction. We used it so that we could represent the work uh, as something times the mass flow rate, and then we could rearrange it in this form. Yeah. That is the work done by the control volume. So that's still like if it's a device that's if it's a device that's expanding, you can still or contracting, you can still calculate that as the integral of PdV. Or uh, if you have electric work going into the device, then you can still calculate that, and since it's coming in, it would be a negative power coming in from electricity. So that's still that is no different for the calculations are no different than the way we've done W dot in the past. That's just our old W dot. But now we also have some work at the inlet and exit, so I'm just putting the CV there to remind you that that's not including the inlet and exit. Okay, so this is a pretty messy equation, right? Who's with me? Yeah. Who? Anybody think it's not so bad? I've seen worse. I'm sure you have. But. Okay, so this is the first law for control volumes. The good news is this simplifies most of the time, quite a bit in a lot of cases. So the first law for control volumes is ugly, but it often simplifies a lot. So if you have an equation that's ugly, but it simplifies a lot, that's what mathematicians call but ugly. Not really. So for a bunch of different reasons, you'll often see that dEdt for the control volume and or W dot for the control volume and or Q dot. I guess I didn't put a CV on that one. And or V squared over 2 terms and or GZ terms are 0. So now I'm going to just go through a list of all the reasons that you can eliminate terms. Okay. Okay, so first, let's think of all the reasons that the rate of heat transfer would be 0. So Q dot is equal to 0. Okay, so what are some reasons that you wouldn't have any heat transfer? The most obvious one is the thing is well insulated. Um, but another thing that happens a lot is if you have something moving pretty quickly through a device, like a nozzle or something where uh, the fluid doesn't have much time to lose energy through heat, then this is going to be 0. So if the fluid moves quickly through the device, then you can often assume that there's negligible heat transfer. Um, Third, if there's a small temperature difference with the surroundings, then even if it's not moving that fast, there's not going to, you lose a lot more heat through a window in the middle of winter than you do in the summer or whatever, or in the, I guess, say in the spring or whatever, because there's not much temperature difference, and that means that the rate of conduction is a lot slower. So if there's a small temperature difference with the surroundings, by the way, all this stuff, this is heavily quizzy material. This is heavily quiz laden. Yeah. And then the last one is if the device has a small surface area. So the control, as call it. Then that reduces the amount of heat transfer that you get. Yeah, just think of it as like the smaller it is, the less you have to worry about it. It's always an issue of just how much. So if you're going to call this 0, it's sort of how much precision do you want? Okay, so logic wise, do these all have to be the case, or do these any one of these can do it, right? So any of the following will make that happen, and you can drop out that Q dot. Okay, now let's think about what about W dot for the control volume, setting that equal to 0? So first, if there's no displacement of the boundaries, that's if this device is rigid. Second, if the device isn't connected to any kind of rotating shafts that come out into the surroundings. Um, and the third one is no electric power is being delivered to the device or used in the surroundings coming from the device. No electric power transfer. Okay, so logic wise, what's the deal here? Is this equal to 0 if, yeah, this time it has to be all of those. Any one of these not being true, that's work you have to deal with. Um, okay, what about uh, dEdt for the control volume? When can that be equal to 0? Steady state, exactly, and that's the only time that you can really expect that to come up. But if it's in steady state, then there's no change in any properties over time. That's not saying there's no change in properties from the inlet to the exit. You know, it could be steady with an inlet at one set of pressure and volume and whatever, and the exit at a different set. But over time, those don't change. Um, and then what about kinetic and potential energy? Um, well, when we're talking about like thermal devices, in most applications that you would ever care about, the changes in speed and the changes in height of the material are pretty small compared to the thermal energies you're talking about. And so very often we're going to leave these out. That's not always, but let's just say these are often small changes compared to the other terms. And so we'll often just ignore these. Okay, any questions about any of those assumptions? So now I'm going to go through a few common devices, and I'm going to go through sort of this thought process, see what we can cancel. Now, these aren't universal rules for these different types of devices, but they are um, sort of they're sort of rule of thumb type rules for each of these devices. So when you get so the first ones we're going to talk about are nozzles and diffusers. Okay, and what I'm trying to say is when you see a problem with a nozzle or a diffuser, you're going to have to go through and look at the assumptions they tell you to make and zero out things on your own, and they're not always going to come out the way this analysis goes. But this analysis is kind of like a big picture idea of how these things work. Okay. So, okay, nozzles and diffusers. Um, these can be the same exact device, just with the flow direction switched. So if you have flow going in this side and out that side, this is a nozzle. So let's call this state 1 and this state 2. So what happens with the nozzle is the velocity at state 1, is it faster at 1 or faster at 2? Yeah, so uh, velocity at 1 is less than velocity at 2. And then under most simple conditions, there's a relationship between the speed of flow of material and the pressure, and it's an inverse relationship. So the pressure at 1 here is higher than the pressure at 2. Okay, so that's what's happening with the nozzle. Yes. Uh-huh. um, so that fact comes from the Bernoulli equation, it's called. It's sort of a simple uh, fluid dynamics equation. Sometimes people bring that up in passing in physics 1. Have you ever heard of that before? And that'll tell you exactly this. It says on a fluid streamline, there's a relationship between speeds and pressures that does that. I think, like intuitively, think of it like this: that the molecules, the fluid molecules, are being like, it's hard for them to get out of that fin. It's easy for them to get in here, but hard to get out there. So they're getting jammed together more and more. You know, get off me! And then they shoot out, and I'm free. Okay, so high pressure here, low pressure here. And then if the fluid flow is going the other way, so this is state 1, this is state 2, this is a diffuser. And everything's exactly reversed here. Yeah. Mhm. So everything's coming into this cylinder. You can imagine this like continuing, you know? And the pressure is building up more and more as this stuff gets closer to the nozzle. And then as it shoots out the nozzle, the pressure goes down and the speed goes up. The diffuser, like you would imagine, is exactly the opposite of this. Um, so V1, so a diffuser slows it down and increases the pressure. So V1 is greater than V2, and P1 is less than P2. You can remember all 4 of those relationships easily if you just remember that uh, high velocity equals low pressure and vice versa. And then just ask yourself what happens to the velocity of the fluid and if it's doing each of these 2 things. Okay, so the most common assumptions. And this will work this is true for both of these 2 things. As you can imagine, the calculations are the same. It's just you switch where the values are. And remember that when you do problems, you want to go through the assumptions carefully yourself. Okay, so let's go through. So what are the some of the things that we can expect here? The first thing is there's not going to be, in most cases, any change in height or any change in height that's like uh, significant compared to the other terms. So uh, there's, we're not going to worry about the height change, and so therefore um, we can get rid of both of these. There's not going to be any change in that's not. There's not going to be any change in dz. Okay, so we can just cross both of those out right away. Okay, that's not saying like, well, if the one at the inlet is the same as the one at the exit, then they cancel each other out. So just don't even worry about it. Second, we're usually going to evaluate these in steady state. And so the time rate of change of the energy is going to be equal to 0. Third, these things are rigid. So there's not going to be any work done by the boundaries. Fourth, we're talking about fast flow through these devices. And so there's not going to be any significant heat transfer. And fifth, okay, well, this one, maybe I should have put this one up here. This is also because of steady state. So what steady state says is that no properties change over time. Okay, and remember what the mass rate balance says about steady state? What does it say about the mass flow rate at the inlet versus mass flow rate at the exit? They have to be the same. And so mi dot is the same as me dot, and we'll just call it m dot. Okay, so let's write this equation, and then we'll just cross out terms because everyone likes crossing out terms. Okay, so there's our starting point. This is 0. Q is 0. W dot is 0. We're just going to call this m dot, and we're going to call this m dot. H, we don't know anything about. VI, we don't know anything about. VZI is 0 in both of these. And so we can rewrite this equation as m dot times HI plus VI squared over 2 is equal to, let me just, Okay, so 0 is equal to m dot times hi plus vi squared over 2 minus m dot times the quantity he plus ve squared over 2. And if you rearrange that, I think the most useful form, well, now you can divide everything by m dot. And I think the most useful form is the enthalpy at the inlet minus the enthalpy at the exit is equal to the speed at the exit squared minus the speed at the inlet squared divided by 2. So the basic idea of um, of a nozzle or diffuser is exchanging enthalpy for speed, or vice versa. We're exchanging them because, these are both differences, but the one on the left is the inlet minus the exit, and the one on the right is the exit minus the inlet. Okay, so a high starting enthalpy leads to a high exiting speed. A high exiting enthalpy leads to a low exiting speed. So this is the idea for sort of like if something just says, if it doesn't give you any data to work with, but it gives you a way to calculate this stuff. This is sort of a back of the envelope approach to dealing with nozzles or diffusers. But most of the time in problems, you're going to have information that lets you cross out terms on your own and do the careful calculation, and then you want to do that. Yeah, it's supposed to be that way because I move one to the other side of the equation. Yep, works out, does that? So HI minus HE. Yep, that's right. Yes, that's right. Um, but remember in the tables, like we haven't had really a reason to look up enthalpy before, but enthalpy is a term in the tables. So just like you can look up U and V, you can look up enthalpy for a given temperature and pressure. Or if you're in saturation, you can look it up for a temperature or a pressure. Uh-huh. Let's see, how long will that take? All right, let's do a simple example. Let's say that we have a nozzle. Um, and steam enters at the inlet. at an inlet pressure of 40 bar and an inlet temperature of 400 degrees Celsius and a speed at the inlet of 10 meters per second. Here's a question. Here's an intuitive question. Will this burn you? Yes, very badly. Don't touch it. So no Q dot, no change in potential energy. So those are just given in the problem. And through the whole thing, the mass flow rate. So we'll assume that it's steady state. The mass flow rate is 2 kilograms per second, and it's steady state. So we're going to use that to eliminate the rate of change of the energy. And then at the exit, PE is 15 bar, and the speed is 665 meters per second. That's super fast. And we want to calculate the exit area. Is that all? Yeah. Okay, so let's start with the full equation and cancel stuff. I mean, this might seem dumb, but every time you write it down, you're ingraining it in your head. So dE dt is equal to Q dot minus W dot for the control volume plus MI dot times the quantity HI plus VI squared over 2 plus GZI minus ME dot times the quantity HE plus VE squared over 2 plus GZE. The potential energies we don't have to worry about. There's no heat transfer. It's a rigid device, so this goes away. It's steady state, so this goes away. MI and ME dot are both the same thing. Those are both 2 kilograms per second. And so in this case, we end up with that simplified form that says H inlet minus H exit is equal to V exit squared minus V inlet squared over 2. At the inlet, we have a temperature of 400 Celsius and a pressure of 40 bar. And so that's enough to look up the enthalpy. And so the table says that H at the inlet is 2992.5 times 10 to the third joules per kilogram. at the exit, so look at what we have at the exit. We don't know the temperature at the exit. We don't know the enthalpy or anything like that. So we don't have enough to use the table. Right? We would if we knew it was saturated, but we're not told that. So let's just plug what we know into this equation and see what we can work with. So we have this equation that says, we have this equation here, HI minus HE, blah, blah, blah. So we have that 2992.5 times 10 to the third minus H at the exit equal to 665 squared minus 10 squared, all divided by 2. And we can use that to calculate the enthalpy at the exit. And you get whoops. Sorry, I gave you a wrong, I read the wrong part here. So the enthalpy here at the inlet, if you look it up in the table, it gives you 213.6 times 10 to the third. So change that equation too. Then what you calculate is at the exit is the one that I gave you before. So the enthalpy at the exit is 2992.5 times 10 to the third joules per kilogram. And now how can we use that to calculate? We're trying to calculate the area at the exit. How are we going to do that? Well, we know that m dot, and that's given as 2 kilograms per second, is equal to the area at the exit times the speed at the exit divided by the specific volume at the exit. And now we have two properties at the exit, so we can look up the specific volume, not in the way that we're most used to doing, but it's sort of, so now we can look this up using pressure of 15 bar and an enthalpy of 2992.5 times 10 to the third. And what you get is, so if you look that up, you get specific volume at the exit is 0.1627. And that is times 10 to the minus third. That's meters cubed per kilogram. And so then use this formula and you get the area at the exit is equal to 2 times 0.1627 times 10 to the minus third divided by the speed at the exit, which is 665. Oh, no, sorry. There's no times 10 to the minus third there. This isn't a liquid. Okay, so it's still going to be pretty tiny. So what do you get for that area? I guess my answer is probably right here. So 4.89 times 10 to the minus fourth meters squared. Okay, so if you're designing this nozzle and you know what your operating parameters are going to be, and you need to know how small to make the exit opening, this is the calculation you would do to calculate that. Any questions? Okay, have a good weekend.